Insolation, pronounced the same as Zones corn insolation, is the measure of solar radiation received on a given surface area in a given time. Conditions on a clear day are assumed to be 1,000 watts of solar energy. This is after all the losses through the air and everything. At the Earth's surface, we call it one sun. It's just a standard that they've put together. One sun, 1,000 watts per meter squared.
So let's just call this panel 1 square meter for example purposes. 1,000 watts of solar power. That light, you know, if we converted that solar power 100% to electrical energy or electrical power, we could run, you know, 10 100-watt light bulbs. But the fact of the matter is we're converting sunlight to electrical energy at about 15%, 10 to 15% in the field. So, you know, a 1 square meter panel is going to probably provide enough power at peak sun to illuminate a 100-watt light bulb, 150-watt light bulb, something like that. So that's the nature of the efficiency, the conversion efficiency. But at sea level, on a clear day, with the surface facing the sun, you're getting about 1,000 watts per square meter.
There are times when you can get more than one sun and less than one sun. When this becomes an issue is during colder temperatures, we have more than one sun available. So you go from 800 to 1,200 watts. It depends on the cell temperature. 800 watts is less than one sun. 1,200 watts is more than one sun, which can happen if the module is cooled below 77 degrees Fahrenheit. Power output goes up.
Okay, now there's some issues where higher altitudes, reflections off of snow, water surfaces, exceptionally clear days, that you can see higher levels, and that's been accounted for in the National Electrical Code in the sizing calculations for your conductors, that these things can operate at levels higher for a certain period of time, and that's certainly something that needs to be accounted for in the circuit sizing. So this is the deal. We get 1,000 watts per square meter, and coincidentally, this is what they use for the rating conditions. So every nameplate rating on the back of the modules is all based on this 1,000 watts per square meter solar radiation level. So if the sun is up for 12 hours a day and the average solar power is 500 watts per square meter over 12 hours a day, what's the total amount of peak sun hours equivalent? Be 6, right? 6,000 watt hours per square meter, or 6 kilowatt hours per square meter.
There are internet sites to look up the number of peak sun hours in locations around the world. You can find a link at www.pvwatts.org. Here are some sample calculations that show how to use the estimated amount of insolation to calculate the power output from a PV array. If the solar power on a module averages 400 watts per meter squared for 12 hours, how much solar energy is accumulated? Multiply 400 watts per meter squared times the 12 hours of sun. It equals 4,800 watt hours per meter squared. There are 1,000 watts in a kilowatt, so divide the 4,800 watt hour per meter squared to get the kilowatts per meter squared. This gives you 4.8 kilowatt hours per meter squared. 4.8 is also the number of peak sun hours. The amount of solar energy collected on a surface over 8 hours is 4 kilowatt hours per meter squared. What is the average solar power over this period? 4 kilowatt hours per meter squared divided by 8 hours equals 0.5 kilowatt hours per meter squared. To get the answer in watts, multiply 0.5 times 1,000, since there are 1,000 watts in a kilowatt, and the answer is 500 watts per meter squared. A PV system produces 6 kilowatt hours AC output at peak sun and average operating temperature. How much energy is produced from the system per day if the solar energy received on the array averages 4.5 peak sun hours? 6 kilowatt hours times 4.5 hours per day equals 27 kilowatt hours a day.